Now let us come to the Valiant-Vazirani's theorem. Okay. So let me state the next claim, or maybe let me call this as a lemma. Let's call this as lemma 5. Okay. So okay, so before proving this lemma, we can actually prove one case of the theorem, which is easy to see. So if 0 to the power m belongs to S. Okay. So suppose the all 0 vectors belong to the set W. Then what can we say? So if 0 to the power m belongs to S, I know that with probability, so if I choose m vectors with probability at least 1/4, I know that they are all linearly independent. If they are all linearly independent, what can I say about this space? Are linearly independent. If they are linearly independent, what can I say about the size of this space? So by just applying this, what do I get? Huh? Exactly. So it is 1, and the subspace which has size 1 is the basically the only 0 subspace, right? So this contains this has size 1. So yeah, so this is basically the space which has the all 0 vector. And now because S belongs to because 0 to the power m belongs to S, so therefore S of m, which is nothing but S intersection with all these sets, is equal to 1, right? So this is the easy case. Now we assume that 0 to the power m does not belong to S. Okay. So our next lemma will be under that assumption. Okay. So if let 0 to the power m be not in S, S has rank some k, and W be a vector that is chosen randomly from 0, 1 to the power m, then the probability that S intersection HW is not empty, given that S is not a subset of HW, is at least 2 to the power k minus 2 divided by 2 to the power k minus 1. Okay. So we want to find out that, well, if I take, so essentially what I am trying to estimate here is that I want to yeah, so I want to look at the sequence, right? I want to look at the sequence from S0 to S1 to S3 and so on. So at any point in time, what I am doing is that I am looking at the previous S and I am doing an intersection with the space HW for the next W, right. So I want to estimate the probability that when I do that intersection, what is the probability that that set will still remain non-zero. Okay, that is when I do when I take W1 and I do S intersection W1, it remains non-zero. Then I will set that to be my new S and I do that intersection HW2, that will also remain non-zero, given the fact that S is a subset of this. So I want to estimate this probability over here. How do we do this? So we will do this by again counting. So let's look at a equivalent condition. So S not a subset of HW, what does that mean? So S not being a subset of HW, so what does it mean to say S is a subset of HW? It means that all the E1 up to EIs belong to HW. So S not a subset of HW means that there is some EI, there exist I such that EI is not in HW, correct? Because if all the EIs belong to HW, then S will also belong to HW, because S is spanned by these EIs. So there is some I which does not belong to HW. If there is some I which does not, and this is if and only if, right? The other direction is very obvious, that if an EI does not belong to HW, then of course S, the direction, yeah, of course, if there exists an I such that EI does not belong to HW, then S does not belong to HW. That is very clear. I mean, at least one vector does not lie over there, right? Now, what does this mean? This means that what would be the form of W? So what does it mean to say that EI does not belong to HW? So HW is all those vectors which are orthogonal to W. EI does not belong to HW means that EI is not orthogonal to W, which means that EI dot W is equal to 1, right. So let me write this, EI dot W has to be 1. There exists an I such that EI dot W is equal to 1. So if EI dot W is equal to 1, what does that tell us about W? W must have, because EI has only 1 at the ith position, everything else is 0, it means that W must have a 1 at the ith position. So there exists a position I in W which is 1. So therefore I can say, another way to say this is that W is not of the form 0 to the power k, 0 1 to the power m minus k. So the remaining, the last m minus k positions can be anything, I don't care, but in the first k position W cannot have all zeros, right. There has to be a 1 somewhere. That is exactly what this is. Okay. And how many such vectors are there which satisfies this condition? Exactly. So there are total of 2 to the power m possibilities, total of 2 to the power m. W is not of this form. So this form means that there are 2 to the power m minus k vectors. So W has a choice of being any of those 2 to the power m minus 2 to the power m minus k vectors. Okay. Now, so this is so we have given a combinatorial interpretation of this condition. Okay. So now let us look at the combinatorial interpretation of this condition, okay, because we want to estimate probability. So therefore it is easier if we can get a combinatorial interpretation, right. So S intersection HW non-empty, what does that mean? So, it means that, well, there exists I such that, okay, EI must belong to HW, because if all the EIs does not belong to HW, then S intersection H will be empty, right. So, there has to be some I which will belong to HW. Now, what does that mean? If EI belongs to HW, then by this same result what we have is that EI dot W is equal to 0, and EI dot W equal to 0. What does that mean? It means that at the ith position W must have a 0. Okay. So, therefore, it cannot be that W is of the form 1 to the power k 0 1 to the power m minus k, because if W is of the form it has all ones in the first k position, then no matter which standard vector you multiply it with, it will always be 1, and that cannot happen, because if that happens, then for all I, EI will not be in HW. If for all I, EI is not in HW, then S intersection HW is empty. Okay. So, therefore, for these two conditions I have that it is not of these two forms. Now, we come to the probability estimate. So, the probability that S intersection HW is non-empty given S is not a subset of HW is at least probability A given B is probability of A intersection B divided by probability of B. So, probability of A intersection B is that both these two events happen, that is W is not of this form as well as W is not of this form, right. So, therefore, from these two M choices I am ruling out 2 times 2 to the power m minus k, at least these many. There can be some commonalities which can actually reduce this, but at least there has to be this many vectors which are not of this form and not of this form. Okay. And the denominator is fixed, that is probability of B, which is 2 to the power m minus 2 to the power m minus k. Okay. So, actually I mean the correct way to look at it is that both the numerator and denominator is basically this divided by 2 to the power m and this divided by 2 to the power m, but that cancels off. So, I get this, and now if you just simplify this, you will get 2 to the power k minus 2 and 2 to the power k minus 1 as we want. Okay. So, essentially what is the idea here? The idea is we are kind of counting how many bad vectors are there for each of these two cases. Okay. And we see that there are the same number of bad vectors, and therefore, this works for us. So, now the last lemma that we need, we call it lemma 6. So, let 0 to the power m be not in S, and W1, W2 be chosen independently at random. Okay. And also let S0 be S and Si be S intersection with HW1 up to HWI, then with probability, the probability that there exists an I in n such that S of I is 1 is at least half. Okay. So, this lemma actually looks very close to the Valiant-Vazirani theorem, but the difference, I will tell you what the difference. Of course, the first is we are assuming 0 to the power m does not belong to S, because the other case is taken care of. The other important point here is that here we are not putting a bound on this, we do not have a bound on these, on this sequence. If you look at Valiant-Vazirani, it says that there exists, so in a set of m vectors there exists an I less than or equal to m such that this condition happens. Okay. Here we are saying that there will be some I for which this happens. Okay. We want to just estimate this, and then once we have proved this, we will show that actually we can work with I at most m minus 1 only. We do not even have to go to m minus 1 would suffice. Just make sure I have it correct. Yeah, of course, I did not say here that S is a subset of 0 1 to the power m. That is anyway the assumption. And another difference is that we are actually proving something a little more stronger. So, instead of 1/4, we are actually showing it to be greater than half over here. Okay. So, it is a slightly better result. So, how does the proof go? So, the proof will be by induction on the rank of S. Okay. So, let rank of S be equal to some k. So, the proof is by induction on k, and what we will show is so our inductive hypothesis will be the following. So, our inductive hypothesis is that probability there exists I in n such that S of I is equal to 1 is greater than or equal to 2 to the power k minus 1 divided by 2 to the power k minus 1. Okay. Now, if you actually take any value, so if you take any value of k that is greater than or equal to 1, you can actually work this out, that this would be how much? So, this will be greater than half for all k greater than or equal to 1, because if you take k equal to 1, then this is exactly half, and as k keeps on increasing, this quantity actually keeps on going towards 1. Okay. So, for k infinity, I think this limit tends to 1, right, as k goes to infinity. It starts off at 1, is it? So, here I have 2 to the power 0, which is 1, divided by 2 minus 1 is 1. So, yeah, so it starts off at 1 and then the limit goes to half, correct. So, the limit, yeah. Okay. So, this is what we will prove. So, now the base case. So, in fact, we can say the following, that if first of all k equal to 0 is not possible. So, what does it mean to say k equal to 0? Rank of S is 0. Rank of S is 0 means that S has only the all zeros vector, but our assumption is that all zero vector is not in S. Okay, is not possible since 0 to the power m is not in S. Now, if k equal to 1, then rank of S is equal to 1. Rank of S is equal to 1 means that S has only one vector, right? So, therefore, S0, which is S itself, is of size 1. Now, the induction step. Okay, so we assume it to be true for k minus 1 and we will show it to be true for k. Okay. First of all, the following claim that with probability equal to 1, there exists I such that rank of S of I is strictly less than k and rank of S of I minus 1 is equal to k. Okay. So, essentially what we are saying is that if I take this sequence, okay, now initially of course rank of S0 is k. Now it can happen that after I take S intersection HW1, the rank stays k. So, at some point I am bound to meet with a Wi such that its rank decreases. Now, why is that? Why should this happen with probability 1? So, again the reason is that see the probability that when I choose a vector it does not decrease its rank is some probability that is less than 1. Okay. So, if I choose a vector and the rank does not decrease, the probability of that happening is some value that is less than 1. Now, I have this product operator. So, what is the probability that none of the vectors in this sequence reduces the rank? Okay. So, it is basically that probability times itself and so on. So, now let us say that probability was p, it is actually basically p times p times p, it keeps on going, right. And this is a geometric series that actually tends to 0. Okay, this is a geometric in fact a sequence, not a series, this is a geometric sequence that tends to 0. Okay. So, if I look at the ith W, the probability that none of the Wi's, none of the Wj's up to Wi decreases the rank is some 1 over p to the power I. Right. So, it never happens, the probability of that happening is 0. Therefore, with probability 1, the complement event is that there is some I which will reduce the rank at some point. Okay. So, let I be the first such I, that is till S minus 1 it did not reduce and at Si it is reducing. Okay. Okay. So, this I mean this argument is again similar to saying that if I do a sequence of coin tosses, okay, what is the probability that I will get some head? That is always 1. Okay, because the probability that I keep on getting tails is a geometric sequence that tends to 0. Same idea. No, there is no bound here. Yes, it can go. But then we will show that, yeah, so then what we will show after this is that, well, the probability that, so here actually Wi's can be anything. But then we will show that if they are actually linearly independent, then there is a bound. And then we will use this result that the probability that they are linearly independent is something. So, now multiplying these two, I get a bound as well as I get a I get a bound by this and I get a value of the probability by this argument. Okay. That is the last part. Yeah, so I will be using this, but anyway we can So, if rank of S I minus 1 is less than k, what does that mean? So, if rank of S I minus 1 is if rank of S I minus 1 is equal to k and rank of S I is less than k, it means that S I is S I minus 1 is not a subset of H W I, right? Because if, assume the converse, suppose if S I minus 1 were to be a subset of this, then S I, which is actually equal to S I minus 1 intersection with H W I, okay, will be equal to S I minus 1, right? And the rank of S I minus 1 is k, which means that the rank of S I will also be equal to k, but that contradicts our assumption. Therefore, S I minus 1 has to be a subset. Okay. So, now we have that S I minus 1 is a subset of this. So, now so now we can apply lemma 5. So, by lemma 5, what do we have? That the probability that so now what is my S? My S is S of I minus 1, S of I minus 1 intersection H W I is not empty, okay, given that S is a subset, S I minus 1 is a subset of H W I, but that anyway we get, okay. So, this thing is anyway happening for us, okay. So, the probability of this happening is greater than 2 to the power k minus 2 divided by 2 to the power k minus 1. And what is this quantity? So, this quantity is nothing but S of I by definition. So, now we can apply the induction hypothesis, because now where have we come to? We have come to a set which has rank now less than k, Si has rank less than k, okay. So, now we can apply the induction hypothesis. By induction hypothesis, probability that there exists, let me call it J belonging to N, such that S of I intersection with H W I plus 1 intersection up to H W J is equal to 1, given that S of I is not empty, is greater than or equal to. So, Si had rank less than k. So, therefore, this will be greater than or equal to where is our induction step? 2 to the power k minus 2 divided by 2 to the power k minus 1 minus 1. And now, if I combine these two, I get that probability there exists I in N such that S of I has size 1 is at most the product of these two, 2 to the power k minus 2 divided by 2 to the power k minus 1 times 2 to the power k minus 2 divided by 2 to the power k minus 1, and this exactly turns out to be 2 to the power k minus 1 divided by 2 to the power k minus 1. Okay. So here I can take a 2 common outside, so these 2 will cancel out, and here I get 2 to the power k minus 1 and divided by this. So this proves the lemma 6 for us. So now we come to the final conclusion of Valiant-Vazirani theorem. So okay, now with probability greater than half, W1 up to Wm minus 1 are linearly independent. So if I choose the set of some m minus 1 vectors with probability greater than half, they are linearly independent. We have already seen this. Now what can I say about the size of this set? So first of all, what can I say about the size of this part only? This will have size how much? So 2 to the power m minus 1, which is 2, right? And now I intersect that with S. So what is the size of this at most? Huh? Now we know that S does not contain those. So this I mean this has size 2, but one of those vectors is the all 0 vector because this is a subspace, and we know that S does not contain the all 0 vector. Okay, so therefore this set cannot be of size more than 1. Okay. Yeah. Lemma 6. Probability that there exist okay, I less than or equal to m minus 1 such that okay, S of I is equal to 1 given that W1 up to W m minus 1 are linearly independent is greater than half. Okay, that is what we showed, that if I have this so given that they are linearly independent, the probability of this happening is greater than half. So now I just multiply the two. So therefore the probability that there exist I less than m minus 1 such that S of I is equal to 1 is at most 1/4. Okay. So of course there are many ways. So if I choose a sequence such that it is linearly independent, okay, the probability that I get this to be less than I mean I get an SI that is equal to 1 is greater than or equal to half, and the probability that they are indeed linearly independent is another half. The probability of both those events happening is at least 1/4. Okay, and this completes the proof of Valiant-Vazirani. Okay. Okay, so that's all. So any questions? So have you seen Valiant-Vazirani earlier in complexity? So you must have seen, I had done this. So basically it is used to show that well, it gives a random reduction from SAT to USAT, right? And the idea is that so there the set of, so there the set S is basically the set of solutions. So from a set of solutions, from a set of arbitrary number of solutions for SAT, you do this set of you do this keep on doing this dot product, and you arrive at a set which has a unique solution, right? So that is how it works over there. And here also the idea is that from a set of what do I say, so well, S is a any arbitrary set of vectors for us. So for our case it is basically those indices that we had, that we considered last time, the number of indices for which I mean the number of indices which are 1 in an OR gate. Okay, how can I get to another I mean how can I convert it to a case where I have only one index which is going to 1. Okay. I keep on doing this dot product and I arrive at that. Okay.